In this video, I introduce improving Wasserstein GAN with a gradient penalty. Wasserstein GAN uses Wasserstein distance to replace KL or GS divergence to stabilize GAN training. However, WGAN requires that Wasserstein distance is measured in a compact space of one Lipschitz functions. For example, distance between two distributions is measured in a Lipschitz space. Given two metric spaces x dx and y dy, where dx is a metric on the domain x and dy is a metric on the domain y. Function f from x to y is a Lipschitz continuous if there exists k is larger or equal to 0. x1 and x2 in the domain x satisfy this equation, where k is a Lipschitz constant. Wasserstein distance is defined as a maximum difference between two expectations. The loss function of WGAN is a minimum maximum problem. WGAN uses weight clipping from minus C to C on the discriminator D so that weights lie in a compact space. WGAN optimization is difficult because of interactions between weight constraint and cost function, which requires carefully tuning of the clipping threshold C for a specific Lipschitz constant K to avoid either gradient vanishing or exploding. Alternative way is to use a gradient penalty to enforce the Lipschitz constraint. A function f is one Lipschitz if and only if it has gradients with a norm at most 1 everywhere. So we directly constrain the gradient norm of the critical output with respect to its input. For random samples, x hat, a soft constraint is added on gradient norm, and the objective function is defined as a sum of two parts. The first part is original discriminator loss, and the second part is gradient penalty, in which the model parameters W lie in a compact space. Namely, we measure the distance in Lipschitz space to calculate the difference between two distributions. Distribution P x hat is sampled along straight lines between pairs of points sampled from the data distribution and the generative distribution PG. The optimal discriminator contains straight lines with gradient norm 1 connecting coupled points from PR and PG. The gradient norm 1 is enforced along these straight lines, which results in a good performance. Here is the pseudocode of WGAN with a gradient penalty. We sample x from PR, z from PZ, and random number epsilon from uniform noise distribution. Then we get this x wave, and then now we calculate the x hat using linear interpolation, and then now we get the loss function. For more details, please check with these references. Thank you. Bye.